Hey everyone, I'm Martin from JetBrains, and today let's look at automation in space. Space automation is the module that helps you run your CI and CD activities in space. It helps you build, test and deploy your project to a variety of destinations. It's also integrated with other space modules like repositories, packages, teams and chats. So that means if as part of your build you want to publish a Maven artifact or a Docker image to your package repository in space, that is possible. This also means that if from your build you want to send a chat message or maybe add a notification to a code review, you can do so as well. Space automation is essentially configuration as code. In your repository, you will add a space.kts file, which you can see in the middle of this graphic. And that space.kts file is essentially instrumenting space automation. It's instructing the jobs and steps in those jobs that have to run. Your actual jobs or actual steps in those jobs will run in the execution environment, which right now is a container, but we're also working on virtual machines and functions that you can run. So essentially based on how complex or how demanding your build steps are, you can either choose to run them in a container, virtual machine or function, but right now only containers are possible. On the right-hand side, you see all of the other space modules. Obviously, since your space.kts file lives in the Git hosting on your space projects, that is also integrated because we have to fetch the sources, right? But space automation also integrates with things like code reviews or packages and teams and chats. So you can work with all of those modules as part of your automation job as well. So this means that you could trigger a build when a code review is opened and maybe report back the status to that specific code review based on whether the build succeeds or not. Space automation also works with external APIs because obviously you want to build your project. So whether you are using Gradle or Docker or Maven or .NET or NPM or whatever, you can run those tasks as part of your space automation job. In space automation, everything is code. So the configuration of your entire automation job is going to be code. The UI that you will see in space itself is mostly informative. It's mostly information. So what you will see is all of the details of your build, mostly in a read-only fashion. There's few configuration options that you can actually do through the UI. Most of the configuration is going to be as codes. That's really nice because that means everything is isolated in a branch. So if your main branch has the automation for your production line of work, you can actually have different automation jobs running for different branches. So if you're working on a feature branch and you have to add an additional automation job or additional steps to an existing automation job, you can do so because everything is isolated in a branch. You can see in the code on the slide here that you have jobs and jobs have a name. And jobs run one or multiple steps in a container. So you will see this container hello world on the slide here. Well, this means that as part of this job, we are running one step inside a container that is of the hello world image. You can have multiple containers running. You can parallelize jobs. There's multiple options that you can instrument how your build should run. But at the core, this is the simplest option of creating an automation job, namely having a job and having a step that runs in a container. Let's look at a hello world example of space automation. What I have here is space, and in space I created a project called Automation Examples. You can have any project you want, but as part of this Automation Examples project, we can go to the jobs that we have. I already have a couple of repositories here that are running automation jobs, and you can already see that for the Hello World Gradle repository, I have two jobs, build and run tests and build and run tests using the API. And we can look at the status of the latest build in here. We can also trigger a run if we want. So if we want to rerun this job, we can do so from here as well. Or we can look at the build log instead. If you look at the build log, you will see the raw output of all of the steps in your builds. By default, this will all be truncated to the last couple of lines from the log. But if you want, you can also download the full log and look at everything that happened as part of your automation job. You can also see all of the steps that are involved. For every build, there's always going to be 2 steps, even if you only define one in your actual automation job. The first step is always going to be the Alpine Git container that runs, and that is essentially checking out a repo of everything you have in your source control. The next one is going to be your first step in a job, and that one will give you details about whatever happened in there. This particular job only has one actual step that runs, so we can only see that one step. If you have tests as part of your build, you can look at the results there as well. You can group them, you can filter them by status. So for example, if you only want to see the failed tests, you can do that as well. And yeah, you can get some information about all of the tests that have run as part of this build. Another tab here is parameters, where you can see that your build is always going to be passed some parameters, either parameters that you decide to pass on to your automation job, or system properties that, for example, give you information about the current branch you are on, who triggered the build. So in this case, this was a manually triggered build by clicking the run button there, which repository, which commit ID, etc., etc. Now, let's maybe create a new repository and set up our own first build. So let's create a new repository. I will call it Hello World. No description, just go with a default repository. And in that repository, we can now create a .space.kts file if we want to start. We can do this from the UI here, or you can do this using your IDE. A simpler way of doing things is going back to the jobs, picking the repository that we just created, and then from there create a .space.kts file. This will give us some information about the first job that we want to add. So by default, we have one job, Hello World, that runs in a container Hello World. So if you would commit this one to source control, we would have our first automation job for this repository. If you edit through the web UI, you will also see on the left that there's a sidebar that gives you a lot of information about how you can run, for example, shell scripts, or how you can do a Docker build and publish of images, and a couple of other options. So make sure to explore those options as well, because there's lots of examples that you can essentially copy paste into your automation scripts. For this particular script, I am going to create a second job, and let's say this is Hello World, but more complex. And what I'm going to do is add multiple steps. So instead of just having a job with one step, this job will have multiple steps that run sequentially. So this one will finish much faster than this one, because this one has to run 4 steps as part of the automation job. Next thing I'm going to do is commit this one and say this is the Hello World example. Commit to the master branch, and let's wait for automation to kick in. You will see at the top of the screen that Space is now processing the automation script. What's happening in the background is that Space is validating the entire script that we have here, because that entire script is essentially a programming language. It's written in Kotlin, and it's validating, first of all, that it can compile, but also that all of the jobs and containers and all of the configuration in there is valid. So it will never start a job run if the automation script itself is not valid. We can look at the details of that, but that's not very informative. So instead, what I'm going to do is return to the jobs, to our Hello World repo, and wait until Space finished processing the automation script and we can see the jobs. And there we go. Space has processed it, and we can now see that we have that Hello World job and the Hello World but more complex job. As part of the Hello World job, you will see that there's only one step that will be run, Hello Worlds. As part of the other job, you will see that there's going to be multiple steps involved, and all of the Hello World containers that we configured as part of our script are present there and will give us information about whatever is happening there. And we can even follow live. Once build output starts coming, we can see what is happening as part of our automation job. All right, so most of our jobs have finished, and let's look at some other examples. So from here, we can go again to our script. And in the script, let's make a number of changes. What I'm going to do is configure the resources that this container can actually use. By default, Space will make available 2 virtual CPUs and I think close to 8 GB of memory. But what we can do as part of this build is increase or decrease the amount of resources that can be spent by this particular step in our automation job. So what I'm going to do is, instead of picking the default 2 virtual CPUs, I'm going to use only half a CPU, which is going to be 512. We are using increments of 512 for half a CPU there. So if you want, for example, 4 CPUs, you could do something like this where you say, okay, I want 4 CPUs for this particular container. The other thing that we can do is configure the memory that is required for this particular step. And what I will do is also use only 512 megabytes of memory. Another interesting thing to note is that jobs are triggered by default when someone pushes code to a repository. So by default, your job will start when someone pushes code to the repository. Maybe that is what you want, maybe that is not what you want. As part of a job, you can also configure when it should be starting. So what you can say is, for example, I want to start on git push, and again, by default, that is enabled. But there's a couple of other options that you can do. You could, for example, schedule a build and do something like running a nightly build or a morning build, where we could say, for example, on a cron schedule, we want to start this build at 8 p.m. every single day so that our developers can see whatever happens since the last day that this particular job ran. There's a couple of other options there. So if you want to start a build when a code review is opened or a code review is closed, you can do that as well. So using this start on element, you can configure essentially when the build should be starting. So what have we seen? We have seen that in every repo, you can publish a .script.kts file, and that is going to be per branch, a configuration of your automation job per branch. So if you want to deviate from what you have in your trunk or in your main branch, you can do that in separate branches as well. The script.kts file contains a definition that has one or multiple jobs, and every job can have one or multiple steps that will run as part of an automation job. By default, every job starts on git push, so when someone pushes code to the repository, but you can configure it to, for example, also run on a cron schedule every single morning, or when a code review is opened, or when someone closes a code review, etc. You can also configure resources, because by default, your container will run on a 2 CPU, 8 gigabytes of memory container. Maybe that is too much, maybe that is too little. So using the resources element, you can configure how many resources will be spent for running that particular step of your job. Now let's have a look at running things. In a step in a container, you can run many things. So for example, in that container, you can run a shell script. This hello world container that we had previously was just running whatever the container already shipped as part of the container. But if you want to run a plain Linux, for example, in this case Alpine, you can run a shell script as well and echo to the console or start whatever you want as part of a shell script. You can also run Kotlin scripts. This is quite similar to running shell script, except that Kotlin script allows you to write your builds or write the logic for this particular step as Kotlin. Kotlin is a programming language, which means that you also get access to a lot of the programming language's base classes. So for example, if you want to print something to the console, you can do that easily. But also if you want to make use of an external library, maybe something that deploys to Amazon or Azure, you can also include those things and maybe script that as a Kotlin script. On the slide here, you will also see that we are getting the API parameter passed in. The API parameter gives us access to space automation and space itself. So if you write Kotlin scripts and you make use of that API variable, what you can do is, for example, post something to a chat message or send a message to a chat or maybe close a code review, things like that. So that can be done through that API variable that you get. You can also run the raw container commands. If you have a container and you know what you want to run using the traditional Docker kind of syntax, you can also execute a command and pass it some arguments and run that as well. Lastly, there's also a number of language and framework specific DSLs that you can use. So for example, if you're building Gradle, you can make use of Gradle W and pass it the parameters using a shorthand syntax for a lot of scripts that you would have to write otherwise. Same thing with .NET. You can run a .NET build by making use of the .NET command and then pass it some parameters that you want to instrument your build with. Same for Docker. If you're using Docker, you can build something, you can push the image and so on, and we have nice shorthands so that you don't have to write a shell script or a Kotlin script if you don't want to. You can make use of those language framework specific DSLs. Also keep in mind that everything you write here is Kotlin based. That entire script.kts is Kotlin based, which means that you can make use of variables in a lot of places. You can make use of functions in a lot of places. So you could, if you have multiple jobs, for example, or multiple steps that have to reuse particular logic, you can extract that into a function and then call that function as part of multiple steps. But I'm running ahead here. So far we have seen that you can write your automation scripts in the web UI, but what you can also do is make use of the Space plugin for IntelliJ-based IDEs. It gives you access to repositories, but it also comes with validation for automation scripts. So if you install this plugin into IntelliJ or into WebStorm, you can actually write your automation scripts inside of the IDE, and that's quite helpful. Let's have a look at running things as part of your automation job. Okay, so this is IntelliJ, and I have opened a project that has some code, some Kotlin code, and that has some tests as well. So you can see that there's tests and code that we want to run as part of our automation job. What I want to achieve is that everything compiles, of course, but I also want to achieve that my tests will run. And I can do that by triggering a Gradle build. So what I'm going to do is create a new file called .space.kts. And what that file is going to do is, again, instrument automation in Space. The next thing I will do is add some jobs in here. And let's call that one build and run tests. And as part of that job, we want to run that Gradle build. Now, we could do that using what we have seen so far and trigger our own container and then instrument everything in there using a shell script, for example. We can also use the shorthand Gradle W, which is the language and framework specific DSL that can trigger our builds. So what we want to do is run a build in the OpenJDK 11 container and then trigger Gradle W build, which will in turn trigger the tests that we have. This is everything I need to accomplish the goal that I wanted to achieve. I can now commit this one and say that this is Space automation. Publish it to Space. There we go. And if all goes well, we should now have an automation job running. So let's look at that. In Space, we can see the same thing that we saw before. Space will process our automation scripts, and at some point when everything is valid, it will actually start running the job that we have. So you will see that we now have that build and run tests task there, and our actual build step is waiting to start. Now let's leave this running and let's revisit it at a later point in time, and let's maybe see how else we can instrument our builds. We're back in IntelliJ here, and I want to achieve the same thing that I did here, but using Kotlin script instead. So what I'm going to do is duplicate this job and call it Kotlin script version, something like that. And then refactor our builds that we have there. So instead of using this Gradle W task, what I'm going to do is instrument my own container. I'm going to say this first step of my build should run in an OpenJDK 11 container. Inside of my container, what I can do is again configure resources. So let's say I don't need 4 CPUs, or I don't need the default 2 CPUs. I may only need a little bit less of memory, so we can do that there. Again, not required, but it's always a good fashion, a good practice to limit the resources for your build to what you actually need. Next thing we can do is add a Kotlin script section. The Kotlin script section will again get our API parameter, and the API parameter gives us access to everything that is in Space. So you will see that our build parameters are in there, that the Space API is in there. We can also run Gradle U here. So essentially, if we wanted to achieve just what we had as the previous job, this would be the equivalent using Kotlin scripts. Before, we had a job running Gradle W in a OpenJDK container. Now we have that same container running Kotlin scripts and then running a Gradle W build. Now, since I have access to the API, why not add some additional console messages and say, for example, running in branch, and use the API.get branch, I think it is. Yes, it is. To emit the current branch to the console as part of our build log. So that's an interesting way of interacting with space, interacting with the build log, and doing things there as well. Now, I want to run my Gradle build, and after the build completes, I want to post a message to a space API. So what I can do is use that, or to a space chat channel. So what I can do is make use of that API.space and get access to chats, get access to messages, and then essentially send a message. What I will require is a message recipient, and that is going to be a channel. And I want to send it to a chat channel from name, and I know that I have a channel called CI channel, and use that to direct my message to that channel. And of course, I want to send a message as well. And what I want to send is a chat message.text. Let's replace that as well. And the text is going to be build is running, build number plus my API execution number. So what this will do, actually, this should be build has completed. So what this will do is, again, build my current project, but after it has built, after the tests have been run, I will also send a message to chat. So I'll update my build script, commit this one, and wait for space to kick in and run the automation job. So back in space, we can see that we now have two jobs running. We have our built and run tests using the language and framework specific DSL running our Gradle builds, but we now also have the Kotlin script version running as a separate job in our space automation scripts. If we look at it, we can look at the build log, so we can see what is happening. And again, we can still see that source code will be checked out from our Git repo, and then the OpenJDK container will run with everything that we have in there. I am going to let this one run in the background until it has finished, because the compilation and unit testing is there as well, and quickly dive back into IntelliJ for the last thing that I want to mention as part of this particular demo. So for a container, we can set our resources that we want to use, but there's another thing that we can do. We have seen that jobs can trigger based on the start on conditions. And we have seen that by default, your build will be triggered whenever a git push happens, and that is enabled by default. Previously, we have also seen that you can run this on a schedule, things like that. So for example, if we say we want to use a cron schedule to run this one every single day, we can do so as well. And say, for example, every 8 a.m. But there's something else that we can configure here as part of our job. Instead of defining when the build should start, we can also define what is a failure condition. What do we treat as failure of our builds? So what we can do is make use of fail on. And we can say that, let's first look at the default. So we have a non-zero exit code. Let's maybe write that correctly. The non-zero exit code is the default here. And what that one will do is essentially fail your build whenever there is a non-zero exit code from the Kotlin script or the Gradle build that is happening here. This is enabled by default, which means if your build fails, if the executable returns a non-zero exit code, the build will fail. In addition, you can also say that you want to fail the build when tests fail. Whenever tests fail, this build will now also fail, and you will see a red notification in the UI there. We can combine those, or we can say, okay, I don't care about non-zero exit codes, but I do care about tests failing. So you can configure it like this. Another one that you can configure as a failure condition is the out of memory condition. And this one deserves a little bit of extra information. What the out-of-memory condition is going to do is fail the build whenever the required memory or the memory usage of your container goes beyond what you configured as the memory limit in your resources. This is particularly helpful if you are, for example, wanting to fail your build whenever you are consuming too much memory. That may matter if you are building Docker containers, for example, or Docker images, where you want to guarantee that the Docker image is not using more than, say, 2 gigabytes of memory. If it does, the out-of-memory condition will fail your build, so you know that your container has been using more memory than was assigned to it. Another way of using the out-of-memory failure condition is to fine-tune the resource usage that you have as part of the job steps in your automation scripts. So if you want to fail the build when there's an out-of-memory condition, you can see if the build fails because of that. You may want to increase the memory that is required. If you see everything is fine, you can decrease the memory usage until you reach some point that is actually accommodating the build that you have. In the meanwhile, our build should have finished, so let's maybe return to the browser. All right, our build has indeed finished. We can now see that our build has completed using Kotlin scripts. We have tests that have run as well, so that's a good thing. And you will see that we have a notification in chat that says on the CI channel that this build has completed. So we have successfully used the API to send a message to the CI channel in the chat there. By the way, this is something that you can do. But there's another way of subscribing to certain build results. So what you can do is, of course, use Kotlin script and send a message to a chat box, but you can also subscribe to jobs and say, for example, that you want to get notified whenever a build completes, every build, regardless whether it's successful or not, or only failed builds, whether they are triggered by your commits or whether they are manually run by you. So based on that, you can ask Space to notify you whenever something succeeds or fails based on who committed it and so on. What have we seen? We have seen that there's an IntelliJ plugin that helps you code your .script.kts file. It gives you code completion, it does validation on the build that you have, so that's very useful to not have to wait for Space automation to kick in. You can actually see it in the IDE. We've seen failure conditions with that fail on element that you can use. Essentially say that you want to fail when tests fail, when there's a non-zero exit code, or when your build is out of memory. We have seen that in a container you can run shell scripts, you can run Kotlin code with access to the other Space modules that are available. And we've seen that you can also make use of the language and framework specific DSL. The .script.kts file is Kotlin, so you can use the language. I didn't really show it in the demo, but if you want to extract a function, maybe put that chat message sending inside of a separate function, you can do so as well as part of your automation scripts. Now let's have a look at what else is there. There's many other things in Space automation. There's permissions, there's environment variables and secrets that you can use. You can push packages to Space repos. I can't go into them in full detail, but I will give you a quick overview of what is possible so you can start experimenting with it. So first of all, for every project, you can configure the access privileges for your automation jobs. By default, the automation service will have read access to your Git repos. It can read and write to package repos. It can view automation, view parameters, things like that. If at some point, as part of your build, you want Space automation to also be able to push to your Git repo, well, you will have to update the privileges there. If you want to make use of the Space API that gives you access to responsibilities in a project, you will also have to enable that if that is something that you want to get access to as part of your automation scripts. So you can configure those in here as well. The next thing that we have is environment variables and secrets. Let's maybe first start with the UI part of things. Again, in your project settings, there's a tab called Secrets and Parameters, where you can pass secrets and parameters to your automation script. So what you can do is, for example, configure something that is not really part of the automation job and can change over time. And we can say that we want to have a parameter that is called name, let's say, and that's going to be Martin. If we save this parameter, we can now make use of this parameter in our build scripts. Similarly, we can make a new secret, and let's call this passwords. And if my password is the very unsafe test1234, I can save it, but I can no longer read it. If I edit the password, I can update the value, but I will never be able to see what is in there. So this is a good way of storing access tokens or something else that you don't want exposed as part of your automation jobs. I have a couple of those in here, so I'm going to remove these two. And you will see that I already have a repo URL and a repo password as a parameter and a secret. So let's look at a build and see how we can actually make use of it. So let's go to our other examples, to the files and to the space.kts file that is in there. And let's look at how you can make use of parameters and secrets. So that's this example. In this example, we have a job called secrets and parameters. As part of that job, we are running one build step in a container. And in there, we are making use of parameters to set the environment variable URL to the repo URL that we just configured through the UI. So that is one thing that you can do. The next line there is where we are making use of the passwords. So here we go. We are making use of a secret called repo password and storing that in an environment variable as well. And then during our build, we can, for example, echo it all to the output, which is not very safe in the case of the secret that we had, the password. But still, it goes without saying that you can make use of those values inside of the automation job that you have. Some other things that you can do as part of the builds is, we already saw that you can send a chat message to space as part of your builds, but there's a couple of other things that are available. First of all, let's have a look at building with multiple steps and running steps in parallel or sequentially. So by default, every step will run sequentially. So first of all, our container here will run an echo 1 to the outputs. The next thing we are doing is making use of the parallel instruction and saying that all of the steps or all of the step configurations inside of this block will run in parallel. So we will run a container in parallel with another sequential series of 2 steps. So using the sequential keyword and the parallel keyword, you can instrument how the order of steps in your build should behave. So for example, if you have multiple steps or unit tests and integration steps that can run separately, you could create 2 steps and have unit tests and integration steps run in parallel with one another to essentially speed up the entire process of your full build. Right, a couple of other examples here is that you can also make use of service containers. I already mentioned that you can make use of integration tests and run them in parallel with unit tests and so on. But what if, as part of your integration test, you need, for example, a SQL database to be spun up? Well, inside of your step, you can make use of service containers. So this step will run the Hello World container, but before it starts running, we will also spin up a MySQL server, as well as a Redis server, so that inside of our actual step, we can make use of that database that now has a database and a root password as well, and have that run as a sidecar to our actual container that is running the step that we want to run. Next thing you can do is share files between steps. Very often, especially if you're doing .NET, for example, you may have one container that does a package restore. The next container is then going to do the build, and then the next container is going to run your tests. Well, maybe there are some files that you want to share in between those different steps. What you can do is make use of either Kotlin script or shell script, or just write to the shared directory on every container and write, for example, a file called file.txt with the content hello world to a shared file in there. This is as part of my first step. In my second step of this particular job, what we can do is then make use of that file share again, locate the file.txt, and then print its outputs to the console. So you can share files between the different steps that are available. Last but not least, there's another thing that I want to show you, and that is that you can also make use of package repos in space. You can consume packages, whether they are Docker images or Maven packages or NuGet packages or NPM. You can consume those as part of your builds, but you can also push them out as part of your build. So I have a Ktor samples project here where I have some files. In my space.kts, my automation script, what I am doing is making use of container commands to run a Gradle build and a Gradle publish. That actual publish job is in my actual build.gradle. And inside of that publish job, what I'm doing is publishing my artifacts to the Maven repo that is in the space Maven URL. That's a variable that you get if you want to push packages to your Maven repo. And I am going to make use of two environment variables to authenticate pushing out that package. I'm going to make use of the JB space client ID and client secrets. And those are temporary variables that you get, or temporary environment variables that you get for every automation script that runs, that allow you to access package repo and other services in space using tools that are not inside of that Kotlin scripts section. So we can run this, and as part of this job, we will actually see that our Ktor samples all run. So we are building all of the different apps that are there. And they will all then push packages to the Ktor apps repo that we have here. And you will see that we have, for example, that chat application from previously that is being published into this space Maven repository. You can do the same with Docker, you can do the same with NuGet, you can do the same with NPM. So it's really easy to integrate with that because you can use all of the tools that you are used to and then make use of that JB space client ID and client secrets to authenticate with those services. So what have we seen? We have seen that we can configure permissions for the automation service. By default, we can read from a Git repo, we can read and write to package repos, but that's about it. If you want to use additional APIs that require more specific privileges, for example, to push code from inside an automation job, you can configure those for your automation service. If you want to limit access to package repos, you can do that as well. So there's a number of permissions that you can configure. We have seen environment variables, secrets, and parameters. So that means that if you have an automation job that needs a variable or a secret to be set, you can configure those through the UI and then consume them from within the automation scripts or from within the automation job and then work with them. We have seen that we can publish to space package repos, NPM, Maven, NuGet, or Docker images. We have seen sequential and parallel steps, where you can essentially instrument how many steps can run in parallel or what the order of execution should be for a specific job. We have seen that you can share files between multiple steps in your automation job, and we have seen service containers. So if you have an integration test, for example, that requires a Redis server or a MySQL service to be spun up, you can do so from your automation job as well. Let's talk about billing and limits in space automation. 1 credit equals 1 minute on the default instance that space provides you, which has 2 virtual CPUs and close to 8 GB of memory. It can be configured using that resources element, and you can set the CPU and memory to a higher value or to a lower value. You can go up to 4 CPUs and to more than 15 GB of memory. You can also configure it to a lower value where you only use 1 CPU, for example, and only 1 GB of memory if you want. This will influence how many credits are spent per minute. 1 credit equals 1 minute using that default instance. If you reduce one of the values, you will spend less credits per minute. If you increase some of the values, you will spend more credits per minute. The full details are available in the web help, but just to give you an idea, it's never a bad idea to reduce the resources that your steps need, because that will mean you spend less credits. If you increment them, if it's really needed, you will be spending more credits. During the space beta, you get 10,000 CI credits per month, which means that during the beta, you can run space automation 8 hours a day, 5 days a week continuously with that default configuration. If you reduce the resources, you will be able to even do more. If you need more resources, it will be slightly less, but just to give you an idea, it's pretty good value in the beta. So in summary, what have we seen? We have seen space automation, and space automation is the CI/CD system that you can use in space to run builds, to run tests, and to deploy your applications. We have seen that space automation uses a .space.kts, and that file contains your entire build configuration, your entire automation configuration as code. We've seen that that script can contain one or multiple jobs, and every job can have one or multiple steps as part of that job. Jobs run in containers, and inside of that container you can run shell scripts, you can run Kotlin scripts, or use the framework-specific DSLs to do a quick Gradle W build, for example. We've seen that you can make use of environment variables, secrets, and parameters in your builds, and we've seen that you can publish to space packages. So if part of your build being successful is publishing a package to a Docker repo, for example, you can do so using space automation. We've also seen that you can instrument how space should parallelize your steps inside of a build. So if you want everything to run sequentially, that's the default. But if you want to speed up the automation job and run multiple steps in parallel, you can do so as well. There's more advanced options to share files between steps. You can run service containers for your integration tests and so on. Do check out the web help because there's lots of examples in there. And again, if you're editing the space automation script in the web UI, you will also see some good examples on the left-hand side in the sidebar there.